This is the second part of lecture 9. So, in this part, we generalize mean value theorem to vector valued several variable functions. Okay, so mm, this is page 7, continuation of part 1. So, before going to the theorem statement, that is the generalized mean value theorem for vector valued several variable functions. So before that we recall a definition. So definition definition of line segment. So given two points x comma y, x and y, 2 points, so one can have a unique Euclidean straight line between them. So formally let x comma y belongs to Rn. Okay, then the line segment between x and y, or from x and y, we denote by L x comma y, and this is equal to 1 minus t times x plus t times y, where 0 less than or equal to t less than or equal to 1. So t lies between 0 and 1. So uh, so if you have some point over here, so one can write this point as, so 1 minus t times x plus t times y. So for t equal to 0 it is x, and t equal to 1 it is y. So at time t equal to 0 the point is x, and time t equal to 1 this is y, and for every t strictly greater than 0 and strictly less than 1, uh, it will give some interior point. Okay, so 1 minus t times x plus t times y. So this is called the line segments, and this line segment is unique. This is called Euclidean line segment, or simply uh, line segment joining x and y. So now we are ready to state the theorem. So vector, third item, so vector valued several variables functions. Mean value theorem for vector valued several variables function. So here is the statement, theorem 2. So one can guess what should be the statement from the discussion at the end of part 1 of lecture 9. So this is mean value theorem. Let f is a function defined on some open subset. So S, this is open in open subset of Rn, and values of the function, that is codomain, is Rm. Okay, so this is the function f from S to Rm, where S is open subset of Rn. So this is differentiable. So let this be differentiable at each point of S. Okay, now furthermore let x comma y belongs to S such that the line segment joining x and y, Lx comma y, fully contained in S. Then the conclusion is, then for every A belongs to Rm, there exists some point, let us denote it by C, on the line segment Lx comma y, okay, such that A dot product with f of y minus f of x, okay, this is equal to A dot product with f prime of C acting on y minus x. So note that a prime of C, what is a prime of C? This is linear function from Rn to Rm, and y and x, their points in S, and S is subset of Rn. So y minus x is in Rn. Therefore f prime of C of y minus x, this makes sense, and this is in Rm. Okay, and A is in, and A belongs to Rm. So dot product with A and f prime of C acting on y minus x, that makes sense. And here also f of y minus f of x, this is point in Rm, so A dot product with f of y minus f of x, that makes sense. Okay, so this is the theorem statement. And one more thing, so if this is S subset of Rn, and x is here, y is here, so this is S, x and y points in S, and this is the line segment L x comma y, this is fully contained in S. Okay, so now we prove mean value theorem, that is theorem 2. This is page number 8. So proof of theorem 2. So now let us draw a picture of the domain. Suppose this is S, okay, and subset of Rn, this is subset of Rn, this is origin maybe. So well, if x is a point here, y is a point here, so this is the line segment contained in S. Okay, so L x comma y, and we define u equal to y minus x. Then one can write L x comma y, this is equal to x plus t times u, such that 0 less or equal to t less or equal to 1. Okay, and this is compact subset of Rn contained in open set S. Okay, so this implies, so this is subset of S, this implies there exists some delta greater than 0, such that uh, such that x plus t times u belongs to S for all t belongs to minus delta comma 1 plus delta. So what is this? This is a point on a slide extension of this line. Okay, so if this is the line segment contained in S, then we can extend arbitrarily small amount this line segment so that the extended line segment contained in S. Okay, so now we define, so let us fix a point A in Rm, define a new function f uh, from the open interval minus delta comma 1 plus delta to R. So this is open interval of R. Okay, so this is the real valued function defined on open interval minus delta comma 1 plus delta. This is defined by f of t. This is equal to a dot product with f of x plus tu, and f of x plus tu is well defined because x plus tu belongs to S. Okay, and note that f is continuous on the closed interval 0 comma 1 and differentiable on open interval 0 comma 1. Okay, now by applying theorem 1, we have f of 1 minus f of 0. This is equal to f prime of theta times 1 minus 0, that is again 1. Okay, and this implies, so f of 1 equal to a dot product with f of so at t equal to 1, this is x plus t x plus u, that is equal to y, and f of 0, that is equal to a dot product with f of x, and the right hand side, so here we use chain rule of derivative. So this is equal to a prime theta equal to a dot product with f prime uh, x plus theta u. So this is theta acting on u. Okay, well, and this implies a dot product with f of y and minus f of x, this is the left hand side, and this is equal to a dot product with f prime. Okay, so what is the statement? So we can denote the point by c, f prime of c and u equal to y minus x. So this is u, y minus x, and so where c equal to x plus theta u, and what is theta. So here where theta belongs to open interval 0 and 1. So these are the endpoints. So this theta belongs to this open interval. Okay, so and this is equal to x plus theta times y minus x. So u equal to y minus x. So this is equal to 1 minus theta times x plus theta times y. And this is a point in on the line segment joining x and y. Okay, so this completes the proof. Okay, now we have a remark here, page number 9. So remark, so we have considered function from S to R M, where S is open subset of R n. This is open. Now if m equal to 1, if small m equal to 1, then what we have, f prime of C, this is equal to nabla f at C, and this is equal to d1 f C comma and so on dn f at C. So they're the partial derivatives. Okay, and so if m equal to 1, then function is from S to R, and A belongs to R m, so A belongs to R. So the theorem 2 implies A dot f of y minus f of x. Okay, so this is equal to f prime of C, that means nabla f at C times so this is dot product, so this is acting on y minus x. Okay, okay, so A dot product. So this is the theorem. So theorem from theorem 2 we have this equation. In particular, if A equal to 1, then we have f of y minus f of x equal to nabla f at C acting on y minus x. Okay, so A is equal to 1. So we have this. So this is basically similar like single variable mean value theorem of single variable function. Okay, now we move to the last part, that is application, page 10. So we recall the definition of Lipschitz function. So let f function from S to R m. So if there exists some constant A belongs to R positive constant such that norm of f of y minus f of x is less or equal to a times norm of y minus x. Okay, so this is norm in Rm, so this is norm in Rm and this is norm in Rn, where S is a subset of Rn. Okay, so this happens if this happens for all x comma y in S, then f is called Lipschitz function. Lipschitz and A is called Lipschitz constant. Now now consider uh, so mean value theorem implies for A belongs to Rm, for A belongs to Rm, A dot product with f of y minus f of x equal to A dot product with the following thing: f prime of C acting on y minus x, where C belongs to L x comma y. So when it is applicable, so here one can assume that S is uh, convex also. So okay, so now if norm of A equal to 1, then we have by Cauchy-Schwarz inequality, so by Cauchy-Schwarz inequality we have f of y minus f of x, this is less or equal to f prime of C acting on y minus x, and this is less or equal to m times norm of y minus x, where m equal to summation nabla f k of z. So z belongs to line segment joining x and y. So this is summation is over k equal to 1 to m. So f subscript with k, this is kth component function of f. Okay, and so this depends on z. So m depends on z. So m equal to supremum of mz. Z belongs to S over Z belongs to S. Okay, so this gives sufficient condition. So if these quantities are bounded, okay, so uniformly bounded on S, then the function f is Lipschitz function. So another application, theorem 3. So you know, if a function f is differentiable and f is defined on connected open interval in R, such that f prime of x equal to 0 for all x in the interval, then the function f is constant. So analogous statement for several variable functions. So let s open plus connected subset of Rn, okay, or maybe polygonally connected. So yeah, so open plus connected, that would imply polygonally connected. So I'll explain what is polygonally connected. Let S be open and connected subset of Rn, and f is differentiable function on S to Rm be differentiable. So now if f prime of C equal to 0 for all C belongs to S, then f is constant on S. So proof, so we use mean value theorem here. So S is open and connected means this implies S is polygonally connected. So suppose here we have a point x and here we have a point y. So this is so first of all, so you know the notion of open subsets of Rn. Now what is connected? So one can join, every 2 point can be joined by path. Now if you can join by polygonal path, that is piecewise line segment, okay, so then it is called polygonally connected. Suppose yeah, that is S is open plus connected implies S is polygonally connected. Okay, so therefore for x comma y, any 2 points in S, we have a sequence of finite sequence of points p1, p2 and so on, like pk, such that the first point is x and the last point is y, such that the line segment L pi comma pi plus 1 contained in S. So this is p1, this is p2 and so on, this is equal to pn. So x equal to, so p, this is pk. Okay, now applying theorem 2 on every pair of points p I comma pi plus 1, we have a dot product with, so for a belongs to Rm, a dot product with f of pi plus 1 minus pi f of pi. So what is this? This is equal to a dot product with f prime of ci acting on pi plus 1 minus pi, where ci belongs to the line segment joining pi and pi plus 1. Okay, and this is true for all I equal to 1 to n k minus 1. And summing up these equations, we have a dot product with f of y minus f of x. Okay, and right hand side equal to 0 because f prime of ci this is equal to 0 by the condition of the theorem, and this is equal to 0. Okay, so this happens for all a belongs to Rm, and so this is page 11. Next page is page 12. So in particular, if a equal to f of y minus f of x, we have f of y minus f of x dot product with f of y minus f of x. This is equal to 0, and this implies norm of f y minus f of x square. This is equal to 0. This implies f of y minus f of x equal to 0 means f of y equal to f of x, and this implies f is constant function on S. Okay, so this completes the proof of theorem 3. So this is it. So we stop here.